let's learn about multi-arm bandit, specifically the epsilon greedy approach. And this is definitely an advanced topic, so consider this a short intro. So let's start with the basic idea for multi-arm bandit, which is to exploit the current winner. Let's create current winner or winning strategy, while occasionally exploring other possible winners. And the two keywords here is definitely exploit and explore. So let's take an example. Let's say you have 4 slot machines. And each has a different payout. Each with different payout. And let's say you get to pull, let's say you get 100 pulls across these 4 slot machines. So let's say we have machine A, machine B, machine C, and machine D. And let's say our payout, let's describe the payout in terms of a mean plus or minus some standard deviation. So let's say slot machine A pays out, $5 plus or minus 2. Machine B, let's say pays out 1 and plus or minus 1. Machine C, let's say 20 plus or minus 8. And machine D, let's say pays out 10 plus or minus 10. So that's our setup. Now, what exactly is this multi-arm bandit epsilon greedy algorithm? So step 1 is, let's call it like our initiation step, where we try every option once. So we're going to try option A, and let's say option A, let's say we got lucky and it did 5 plus 2, so let's say it gave us $7. And option B, let's say it gave us $1. Option C, let's say we were unlucky and it gave us 20 minus 8, let's say it gave us $12. And then option D, let's say we got lucky and we got 10 plus 10, let's say it gave us $20. So that's step 1, which is just our initiation step. Now, the algorithm, which is going to be step 2 onward, we could call it, say, step 2, which is going to be the algorithm. The algorithm is going to be 90% of the time, pull the winner. I think it's better to say expected winner. Based on historical data that you've seen from all your previous polls, you're going to pull the expected winner 90% of the time. And then 10% of the time, you're going to pull randomly. So what does this look like? So again, our algorithm says 90% of the time, pull our winner. And let's say we're at 90%, our winner is slot machine D. So let's pull it again. Let's say it gets us, $16. Go to our algorithm, we have it to land into 90%, it says pull the winner. Looking at the historical data, D has historically still performed the best, and let's say it gives us, say $10 this next pull. All right, back to our algorithm, 90% comes up again, says pull the expected winner. Looking at the historical data, again, we're looking at all 3 of these pulls, and on average, these 3 do beat out the other options, so we're going to pull option D again. And let's say we pull out, let's say $10 again. Let's go to our algorithm. By chance, we now got to this 10% pull at random, and let's say we pulled at random, and we told us to go to slot C, and slot C gets us, say, $28. We got super lucky that time. And then back to our algorithm, and it says, let's go to the expected winner. The expected winner this time, let's see, I think it might end up being C actually. Let's see, 12 plus 28, that's 40, divided by 2, that's 20. So this comes out to be 20 in expectation. This is going to come out less than 20 in expectation. Our algorithm says pull the winner, so we're going to pull C again. And let's say it gets us 20. Back to our algorithm, it says pull the winner. Again, C historically has been performing the best. And let's say we got a bit unlucky this time, and let's say we got 15. Back to our algorithm, let's say it sends us to this random. And at random, it sends us to B. B gets us $1. Back to our algorithm, pull the winner. Our winner historically, I think it's still C, so we pull C again. Let's say it gives us $20 again. Back to our algorithm, let's say it sends us to this 10% random. And by chance, it says to pull A. And let's say A gets us, say, $7. Back to our algorithm, it says pull the winner. The winner's still C, so we pull C again. So it gets us $18. So what's going to happen is we're going to repeat this algorithm until we finish our 100 pulls. And let's say after 100 pulls, we pull A 7 times. Let's say we pull B 3 times. We pull C, let's say 50 times. And let's say we pull D 40 times. Again, this polling is based on this algorithm. So what's the payoff after this algorithm? In expectation, in average, these 7 pulls each pay out $5. So on average, you'll probably make $35. And then for slot B, on average, you'll probably make $3. Slot C, 50 times 20, so on average you'll actually make 1,000. And for slot D, on average you'll make, let's see, 40 times 10 on average, 400. So in total, you're going to make about 1,438 using this greedy epsilon algorithm. And again, how this algorithm works is you're exploring the current winner. You're exploiting the current winner. So in this case, D, we were exploiting D for a while occasionally exploring, and by occasionally exploring, we're exploring 10% at a time. We're exploring other possible winners. So when we got down to here, we happen to get the random 10% and said explore other winners or other potential winners. So we explored C, and C actually became our current winner based on historical data. So we started exploiting C, and then we have to explore again because of that 10% random. So we explored B by chance, and it didn't pay out so well, so we kept on exploring exploiting the current winner. And again, we explore A next, still not the highest payout, so we'll go back to exploiting C. And you're going to repeat this algorithm, and occasionally you will go back to D, for example, just by chance, and you're going to probably exploit D a bit as well. And by chance, you'll probably start exploring A and B, that you likely will not exploit them. So I imagine this algorithm bouncing between C and D most of the time, which is why at the end I give an example of 50 polls for C and 40 polls for D. So what's another benefit of this algorithm? So in addition to the exploiting the current winner as well as exploring other possible winners, another benefit is we actually move to winning options, or let's say higher payout options. Much earlier, instead of wasting time on losing options. So you can actually contrast this to, say, an experimentation. With an experimentation, if you had 100 polls, you would probably run your experiment by putting 25 on A, 25 on B, 25 on C, 25 on D, and your payout is actually going to end up being less because you're spent quite a lot of resources on B. You're spending 25 polls on B, and B has been giving you around $1 consistently. Whereas in this multi-bandit option, multi-arm bandit option, we quickly check B during our explore 10% of the time. We notice, hey, payout isn't that great. Let's go back to the winning options, which is C or D. Hence, we tend to move to these winning options much earlier, and we spend more of our polls or more of our resources on these versus wasting too much time on these losing options. And that's a quick intro to multi-arm